Now let's look at trust region policy optimization, which is an advanced policy gradient algorithm. Understanding this paper will give us an intuition into the algorithms that are used in post-training methods like PPO. So the traditional policy gradient methods that we were seeing were trying to maximize the expected return directly by taking a stochastic gradient ascent, that is finding the direction of the gradient of the objective and taking a step proportional to some to that gradient times some learning rate. Now, even though you are taking very small steps in your parameter space, sometimes there can be even a small change in parameter space may not reflect like a small change in policy. Sometimes even a small step in the parameter can degrade the policy performance a lot because the new policy may diverge a lot from the old one. And this can result in something like catastrophic forgetting and a collapse in the policy performance. So TRPO tries to avoid this kind of a collapse while trying, and it is backed by theory, which says that the updates that it makes are monotonic, and even it is more sample efficient since like a small bad step in your vanilla policy gradient can lead to a policy like a degrading policy performance. So you have to take a lot of steps uh, for vanilla policy gradients, making it not so sample efficient. TRPO is much more sample efficient in that manner. So the key equation is that it tries to update its parameters by trying to optimize a surrogate uh, of the objective, which is like to the first order. It is equivalent to that to our objective, which is maximizing the expected rewards, while ensuring a condition that the average KL divergence between the last parameters and the new parameters, like the policies implied by the last and the new parameters, is less than some delta. So let's go through the paper to see how we arrive at this update. So let's start with the notations used in the paper. So the MDP is defined by this tutorial set of all states, the action space, the transition probability distribution from the environment, the reward function, like from state to R, which is like the expected rewards from if you reach a particular state, the initial state distribution, which gives you a probability that a state is the initial like the agent is initialized at a given state, and gamma the discount factor. So now the eta of pi is denoted to be like the objective function which we want to maximize. Like we want to find an policy which maximizes this particular objective, and it gives a measure of the performance, which is like the total expected sum of discounted rewards from t is equal to 0 to infinity. So these q pi, v pi, and a pi are the standard definitions of the action value function, and the advantage. Now, it can be proved that the difference in performance between a policy pi hat and pi is equal to the expected sum of discounted advantages, where the uh, states and actions are sampled from your policy pi hat, and the advantage is computed for the policy pi. Now let's look at a proof of this, which is given in the appendix A of the paper. We want to prove that the difference in the uh, performance of policies pi hat and pi is equal to the expected sum of discounted advantages of the states and actions, where the states and actions are sampled from the policy pi hat, but the advantage is computed for your policy pi. If you look at this expectation, it is equal to summation, like the trajectories are being sampled from pi tilde, summation from t is equal to 0 to infinity, gamma to the power t times e pi of st comma at. Now in expectation using Bellman equation, this can be written as the reward at st plus gamma times v pi of st plus 1, like the action value function minus the value function v pi of st. So this becomes like a telescoping sum. The like gamma times v pi of st plus 1 gets cancelled with the next terms gamma times v pi st. So basically at the end of this telescoping sum, all these terms related to the rewards, like the discounted sum of rewards, they can be collected together, and the initial minus v pi s of 0 also doesn't get cancelled. So this is equal to the expected, like this is equal to the sum of these two terms. Now the expectation can be distributed over the addition, and now the expectation of the v pi of s0 is basically the value function, like how much total expected sum of returns you get from your initial state, which is nothing but the performance of policy pi. And since here this is these total sum expected sum of rewards, where these trajectories are being sampled from pi tilde, it's like the performance of pi tilde. Let's come back to the to page number 2, where we had started. Now we found an equation for the difference in performance between pi tilde and pi, and now let's look at something called the unnormalized discount visitation frequencies. So rho pi of s is the steady state probability of that the agent would reside at state s, where this probability is discounted by gamma. So this is probability that the agent is at state s at 0th time step plus gamma times probability that it is at the first time step plus gamma square probability that it is at the second time step, and so on. So this is unnormalized. So now if we look at this equation again, we were writing that this expectation terms where the states and actions were being sampled from your policy pi tilde. This expectation can be written in the form of like summation from time steps 0 to infinity, probability, like summation for all states. Since we want to sample states and actions from this distribution, it's like probability that you are at this state given your policy pi tilde, since we are sampling from pi tilde, and summation over all actions, probability of choosing this action at this state given pi tilde times this factor, which is gamma to the power t a pi sa. So we can collect this gamma to the power t outside here, and also reshuffle the indices of the summation of t is equal to 0 to infinity and s. And then if we look at this term here, it is the same as rho pi tilde of s. So we replace it with this discounted visitation frequencies, and now we can see that the difference in performance between policy pi tilde and pi is like summation over all s probability, a normalized probability that you are uh, that on a steady state you are at a state S times summation for all a pi tilde of choosing that action at that times at that state S times the advantage a pi of SA. Here advantage is calculated with your policy pi. So this equation implies that if you are making any policy update from pi to pi tilde, it would result in an improvement in the policy if for all states this advantage term is positive, which means that for all states your new policy is leading to higher returns, like the action sample from a new policy are leading to higher returns than the returns from those states uh, when following the policy pi. It also means that the policy iteration algorithm, where you make an update just by taking a deterministic uh, policy, would lead to an improvement, since now if you make a improvement in your policy by making pi tilde s as argmax over all a pi sa. So the term here, which like among all actions, only the actions belonging to argmax would be non-zero, since pi tilde a given s would be zero for the others, and for the action where you updated your new policy as the argmax of the q pi sa, this advantage term will be either zero or positive. This is because the q pi SA would be the max of all q pi SAs, like maxed over all actions, and the v pi s would be an average of q pi SA averaged by the policy pi. Now at this state, we see that we had this term. Now making and optimizing the policy pi using this, which has a term of the state visitation frequencies with respect to the new policy, is very complex and difficult. So in the paper they take a local approximation by replacing the row of pi tilde with the row of pi. So you could try to collect samples from your existing policy and try to improve your improve it to get your new policy. And this approximation, now instead of eta of pi tilde, is replaced by a surrogate function L pi of pi tilde. What's interesting is that this new surrogate of your performance L pi of pi tilde is equal to your eta of pi at pi is equal to pi theta naught. Basically, if pi tilde is equal to pi, the function, this surrogate is equal to your performance parameter, of which it's an approximation, and as well as it's equal in derivatives at when evaluated at pi tilde is equal to pi, which means that at least at first order which means that it's a first order approximation of your performance function. Now, since L is a local approximation of eta, it means that if we are close in, if the new policy is close to the old policy, that is like if you take a sufficiently small step, this would be a good local approximation, which means that trying to improve your L pi of pi tilde like trying would lead to an improvement in your performance eta of pi tilde. So Kakade and Langford in 2002 showed that if you create like a policy iteration done in a specific fashion can lead to improve in performance. So if the new policy is like a mixture of your old policy um, and a pi prime um, where you have like the averaging being done using a parameter called alpha. It would mean that for 1 minus alpha times you'd follow the policy pi old, and like for alpha time you would follow the policy pi prime. So in a way you are still very close to your pi old. It could lead to an improvement in your policy since your performance of your new policy is greater than equal to this uh, function minus a term, and this term would be really small if alpha is small, and also if the pi prime is very close to your pi old. Since epsilon is like the say maximum across all states, the expected advantage uh, uh, of your actions, state actions, where states are being where the actions are being sampled from pi prime. So if the pi prime is very close to pi, this the max across all states of this expected advantage would be small, and if you choose alpha to be small, you can show that your new policy's performance would be greater than equal to the L of pi old of pi new, L subscript pi old of pi new. That is like the surrogate when you're trying to improve from pi old to pi new, which means that improving pi uh, L pi old of pi new is a good way of approximating eta of pi new if your uh, alpha and epsilon are small. However, this type of policy, like the pi nu being a mixture policy, is restrictive in nature, and in TRPO they give a practical policy update mechanism which is applicable to all stochastic policy classes. So while the previous equation showed that the L was a lower bound on eta with some correction, which is very small if alpha is small and epsilon is small, it was restrictive because it was used. It can be only used for it was only a bound for certain class of policies, like which was a mixture of the old and new policy. However, in TRP, they showed they derive a similar bound for general policies, where instead of this mixture, they replace the alpha with some measure of the distance between pi and pi tilde. So first, let's see what's the total variation divergence. DTV between two probability distributions P and Q is half summation for all I, Pi minus Qi. So this gives you like some measure of how different uh, the distributions, probability distributions P and Q are. Now, since a policy has a distribution over actions for every state, d max TV between two policy pi and pi tilde is the maximum of this total variation divergence across all states. So maximum over all state, for every state you have a distribution of overactions from pi and pi tilde. So you find the divergence between them and take a max. That's your d max tv pi tilde. So in they derive in TRPO, they derive that if alpha is the d max tv between pi and pi nu, you can show that the that L pi old uh, L from pi old to pi nu is a lower bound on eta with a correction term minus 4 epsilon gamma upon 1 minus gamma square alpha square, where again, just like before, epsilon is the maximum over a pi SA. So if the um, policies do not vary a lot, and the uh, this particular epsilon is also small, we can show that the L is a lower bound on eta, and since this is a lower bound, improving L would lead to improving eta, which would give you one particular way of finding a policy iteration algorithm. So now there exists a relationship between the total variation divergence dTV PQ and the KL divergence between PQ, which is that the total divergence square is less than equal to KL divergence. So like this from this bound, we can reach a newer like update that bound in terms of the KL divergence, that the um, L from pi to pi hat is a lower bound minus C times the maximum KL divergence across states between pi and pi tilde is a lower bound on uh, eta of pi tilde, where C is 4 epsilon gamma upon 1 minus gamma square. So now that we have this lower bound, and you could have an algorithm like this, like algorithm 1, where for like iteratively you try to do a policy iteration, where the next policy at step I um, is maximizes um, uh, this lower bound that we calculated, um, and you can prove that this leads to a monotonically improving policy, like a monotonically increasing performance uh, across the policy iterations. So now let's look at how to define this for this general policy iteration algorithm for the case where you have parameterized policies. So, say for example, in let's look at the policy pi theta a given s. Here the policy is defined using some parameters theta. For example, these can be the weights of a neural network, or it can be the exact variables that define this policy. So there are some notations that are used in the paper. So eta of pi theta is just written as eta of theta, and the in terms of the dkl between policy pi theta and pi theta tilde, it's just written as dkl of theta tilde. So from the preceding section, we wanted to maximize this from like a given theta, maximize this particular quantity, which was like a lower bound on your um, uh, performance of pi of theta. So one way, if you take the steps which are defined by this penalty coefficient, the step sizes would be really small, and we want to take step sizes which are bigger but are still robust. That is, which do not which ensure that the policy does not change a lot. So this can be approximated by an another constraint optimization problem. where you want to maximize across theta the L from pi theta over to theta, to pi theta, subject to the constraints that the maximum KL divergence is less than equal to some variable delta. So this imposes a constraint that the KL divergence is bound at every point in the state space, because it's like the max across all states. The KL divergence defined by the policy is pi theta volt and pi theta. However, it's again like harder to solve that. So this is replaced by an average KL divergence, where the samples where the averaging is done, or the expectation is done using using the um, pi theta volt to collect the samples and take the expected KL divergence. So this gives you a an algorithm to solve to improve your policies. However, in a parameterized form, that you want to maximize the theta. You want to find the theta which maximizes your L theta over to theta, while constraining that your average KL divergence, where the averaging is done from samples of coming from pi theta volt, to be less than some variable delta. So now the previous section proposed a constraint optimization problem on the policy parameters, which optimizes an estimate of the expected total reward eta subject to a constraint on the change in the policy at each update. So this section describes how you can estimate and the objective and the constraint using samples and expectations, and then this can be used to perform the optimization based on the by solving that constraint optimization problem. So you wanted to maximize this particular quantity, and um, uh, uh, actually there was another term in L pi theta old. There was another term of eta of pi old, which maximizing for theta means that we can drop that term, and then here we want to convert these terms into expectations, so that we can use sampling to estimate this and then perform that constraint optimization problem. So for sampling from all states using this unnormalized uh, state visitation frequencies can be converted into expectation of states being sampled from rho of theta volt by just another factor. Similarly, uh, if we see here, summation over all a pi theta a given as times a of theta volt sa, it can be seen as expectation of actions being sampled from your policy from pi theta of this advantage, and we can do an important sampling estimator, that you multiply and divide this by uh, some sampling distribution q, and then take the expectation, and that integral can be converted into an expectation with respect to q. So this summation can be converted into an expectation. The actions are being sampled from some sampling distribution q of pi theta by q a given Sn of a pi of a theta volt Sn comma a. So now we can, if we are making, we want to find like the best theta to uh, to maximize this quantity subjected to the scale divergence. It is equivalent to an iterative algorithm where you can use the last uh, time steps, like the last policy to collect samples and trajectories, and that can form your queue to collect like your states and actions, and accordingly, these objectives and the constraints can be obtained directly from those samples from previous iterations policy. Coming back to the spinning up blog, we see how this update was derived. Um, and in this policy iteration algorithm, your next update, you try to maximize your objective, which is like the expected advantage times this ratio of probabilities from the old and the new policies, with the constraint that the average KL divergence between the two is less than equal to delta. And the theoretical update isn't easy, so they use some approximations to solve this constraint optimization problem. So they use like a linear approximation of their objective, and quadratic approximation of the constraint, and use some analytic methods to derive the update. Also, since uh, because of the errors that might creep in because of the approximations, and because of the Monte Carlo estimates, so they perform, instead of the exact update coming from this, they perform a backtracking line search to ensure that the new update also satisfies the constraint. So finally, let's look at the pseudocode of the algorithm of TRPO. You initialize the policy parameters pi theta, and the initial value function parameters phi 0. So there are two set of parameters for parameterizing the policy and the value function, and you define the various parameters like the KL divergence limit delta, backtracking coefficient alpha, and the maximum number of backtracking steps k. So this is an iterative algorithm where at each iteration you try to improve the policy. So you For step k, you collect trajectories by running your policy in base like your most recent policy in the environment. Collect the rewards to go, which is like the returns for these trajectories, r hat of t, using your current value of your value function. mm, Compute the advantages for each of the time steps. So now the policy gradient is just the derivative of that, of the first order, or like the derivative of that objective, which is the ratio of the uh, uh, which is equal to like the derivative of log probability of the uh, uh, like the log derivative of the log of the policy, times the an estimator for your advantage, which we had already computed. And and then the next step is to compute the exact gradient update. So using conjugate gradient algorithm, find an approximate value of h inverse of g, and then this is the update step that we want to take, which can be computed like effectively once this is found. However, using backtracking line search, find this update by multiplying this by a factor alpha, which is like and choose the smallest value, which improves the sample loss while satisfying the KL divergence constraint. Now, at using these collected trajectories, we again fit um, the value function using the TD error, using some gradient descent algorithm. So this gives you like a whole algorithm of how to um, how to find iteratively improve your policy using the um, using the objective and the constraints.